This presentation on hydrostatic transmissions is the 7th in a series of 8, which provides a comprehensive introduction to hydraulics, the science of fluid under controlled pressure. I'm Paul Cook for Sperry Vickers. Pumps and motors used in hydrostatic transmissions can be vane, piston, or gear type. Piston units are probably the most common because of their high efficiency and their pressure capabilities, and the fact that they're available in fixed and variable displacement models. Now, let's take a closer look. There are 3 basic types of piston units. In this one, the bores in the cylinder block look like the spokes of a wheel. The pistons move in and out of them radially as they follow the inner contour of the reaction ring. The displacement is determined by the amount the reaction ring is offset from the center line of the cylinder block. In a bent axis pump, the pistons rotate axially within a cylinder block, which is at an angle to the drive shaft. As you can see, the pistons at the top have been pulled outwards, and those at the bottom pushed in. The distance between their relative positions determines their stroke length and displacement as the entire assembly rotates. Changing the angle of the cylinder block with relation to the drive shaft enables us to vary the pump displacement. Finally, we have a unit where the cylinder block is inline. It's driven by the drive shaft. Shoes on the ends of the pistons are held against and slide around an angle swash plate as the drive shaft is rotated. In this case, both the distance the pistons travel in their bores and the pump displacement are determined by the angle of the swash plate with respect to the drive shaft. The piston stroke is reduced as the swash plate is moved towards center. At the center position, the swash plate is at right angles to the drive shaft, and there's no movement of the pistons in or out, and no flow into or out of the pump. Crossing the center with the swash plate would again start the pistons moving, but in the opposite direction, and flow from the pump would be reversed. A piston motor is almost identical in construction to a pump. The operation, however, is quite different. In a pump, the shaft drives the cylinder block, causing the pistons to move in and out of their bores, taking in and then discharging fluid. In a motor, fluid is pumped into the cylinder bores on the inlet side, forcing the pistons out against the swash plate, which, because of its angle, causes them to rotate, carrying the cylinder block and output shaft around with them. While the torque of a motor, like the force of a cylinder, will be only what is required to move or support a load, fixed displacement motors can provide constant torque regardless of their speed. Here we have 2 cutaway models of the units we've been discussing. This one is a variable displacement pump, and here we have a fixed displacement motor. The pump has a lever which can be operated manually to move the yoke. The yoke holds the swash plate in any desired position from maximum displacement in one direction through center to maximum displacement in the other. As the shaft is rotated, we can see the pistons withdrawing from their bores. As they come out, oil enters here, making this the inlet port. Pistons on the opposite side are being pushed in by the swash plate, and oil is forced out of this port. Notice how the piston movement is decreased as the lever is moved towards center. Centering the lever puts the yoke and the swash plate at right angles to the shaft, and the pistons cannot move in or out. Now, if we continue to rotate the drive shaft in the same direction, but move the lever across center, the piston movement and oil flow is reversed. Now, the motor, because it's a fixed displacement unit, has the swash plate angle machined into the housing, and it can't be changed. Oil entering at this port forces the pistons back against the angle swash plate, causing them, the cylinder block, and the drive shaft of the motor to rotate. Oil is discharged from the opposite port and is returned to tank at low pressure. Reversing oil flow to and from the motor would, of course, cause it to rotate in the opposite direction. Now that we have an understanding of how the pump and motor operate as individual units, let's try putting them together. If we could interconnect the ports of our cutaway units, we'd see that by merely moving the pump lever control, we could drive our motor fast or slow in either direction. We could even prevent it from being turned by centering the pump yoke so that it could not pump or accept any fluid. Needless to say, a hydrostatic transmission is not quite that simple, so an illustration might be helpful. Here we have a variable displacement reversible pump and a fixed displacement motor, both shown symbolically. Oil flowing through this line to the motor would cause it to rotate in this direction, and oil through this line would cause it to reverse. So far, so good. But since this is a closed loop, all the oil the pump receives is what returns from the motor, and this could cause problems. As good as they are, both units do have some internal leakage. Adding a small reservoir, pump, and relief valve would enable us to replenish the fluid leaked from our closed loop. But since our system is reversible, we'd need a check valve here and another here. And these are called, you guessed it, replenishing check valves. This not only enables us to have a more responsive system, but sometimes permits the pump to be driven at higher than normal speeds. Of course, there's always the possibility of the motor being overloaded or stalled, so we must have overload protection. This is accomplished by installing cross-line relief valves, which open and divert pump flow back to its inlet during overload conditions. But remember, oil going over a relief valve is energy being wasted, and wasted energy generates heat, and there's no way in our closed loop to dissipate it. So stalling for extended periods must be avoided. For a more realistic view, we have a cutaway of a complete package, including the electric motor which drives the pump. This lever controls the yoke, which contains the swash plate, enabling us to control the amount and direction of pump flow. This, in turn, determines the speed and the direction in which our motor rotates. Flow paths interconnecting the various components are cast or drilled into this section, combining everything we've discussed into one integral unit. If our application happened to be in a remote or hazardous area, the hydraulic motor could be removed and mounted separately with lines running back to an adapter plate at this point. In this way, the pump, electric motor, and other components could be located out of harm's way. Now let's move from our cutaway to a working unit. Right now, the electric motor and pump are turning at 1800 RPM, but there is no movement of the motor shaft. Actually, we couldn't move it if we tried, because the pump yoke is centered, and its pistons can't move in or out of their bores. Moving the lever off-center causes the motor to rotate slowly. The more we move the lever, the faster the motor runs. How fast the lever is moved determines the rate of acceleration and deceleration of the motor, and of course, crossing center will make it reverse. Remember, the pump and motor in this unit have the same displacement, so the top speed of the motor would be essentially the same as the pump drive speed. If we were to install a larger hydraulic motor, it would develop more torque, but since it would require more fluid per revolution, its top speed would be slower. A smaller motor would, of course, turn faster, but develop less torque. In each case, however, the torque would be independent of speed. Okay, that concludes our discussion of hydrostatic transmissions. In summary, these transmissions offer some important advantages. They're flexible and easy to operate. They have high horsepower in relation to package size and weight. They can be stalled without damage. The low inertia of their rotating members permits fast starting, stopping, and reversal with smoothness and precision. The output shaft speed can be varied over the full speed range in either direction, with constant input shaft rotation. This has been Chapter 7 in our 8-part training series on the basics of hydraulics. I'm Paul Cook for Sperry Vickers.